This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Hi, I'm Greg LeBlanc. Welcome to Unsiloed. I'm here today with Guru Madhavan, who is the Senior Scholar and Director of Programs at the National Academy of Engineering, and also the author of this book right here, Applied Minds, How Engineers Think. And Guru also has a new book coming out called Making Better Choices, which is, I think, a very interdisciplinary project where you combine engineering and political science. So welcome, Guru.
Thank you, Greg. A pleasure to be with you.
So I really enjoyed this book because it attempted in a very short period of time to kind of encapsulate, what it is that makes the engineering way of thinking so distinctive. At business school, I've taught in engineering school, I've taught in business school. Most of the students in the business school are engineers. And so I spent a lot of time trying to get them to cross-pollinate their way of thinking with the non-engineers. But then I also spent a lot of time trying to help them unlearn some things that are, essential to the engineering way of thinking. And the more I thought about this book, you mentioned it kind of sort of as an aside, but there seem to be enormous parallels between the way engineers think and the way economists think. So as someone who has both a PhD in engineering and also biomedical engineering, I believe, and also an MBA, you've had an opportunity to see these different ways of thinking at work. So I'm going to ask you to summarize the engineering way of thinking, even though, summary, we're going to have to probably have 4 or 5 different summaries as we walk through. But what is it that makes, the engineering mindset so distinctive?
There are some cosmopolitan roots to how the engineering way or pattern of thinking really emerges or is put into use over millennia across cultures here. And that was the starting point assignment for me as I tried to compose the book. The subject of our discussion today is how the elements of structure, constraints, and trade-offs really fuse to formulate the engineering sensibility across contexts. And briefly, how do you see a structure where there's none? Or a civil engineering professor used to tell me when I was a student, how do you feel the forces of the load-bearing columns? Or how do you feel the pressure through the metaphorical wind tunnel as for a technology or a structure that doesn't even exist in the first place? There's a lot of intuition and tacit knowledge that's involved in this structural, perceptual way of thinking that contributes to the first element. The second one, invariably, any good engineering or any piece of engineering operates under constraints, whether it's finance. I mean, as the saying goes, it's a cost, schedule, technical requirements that often drive the engineering. That's at least how the traditional way of engineering has contributed to the construction and growth of industries and enterprises that support our lives. And finally, trade-offs. It is ultimately, it starts with the cognition and consciousness that you have to make sacrificial judgments no matter what. You just cannot achieve everything in a design, in a solution space as you pursue this. You could trick yourself into the feeling that maybe you gain everything here, but sooner or later you're going to encounter the costs or consequences going forward. So you have to invariably make these explicit trade-offs. So as a combination, structure, constraints, and trade-offs are the essential ingredients of the engineering mindset, as I've come to articulate in this book. But of course, there are broader notions, broader influences that take engineering in different directions, unexpected directions, purposeful, deliberate, sometimes unintentional. So that's those are the kinds of elements one has to think about in a responsible engineering profession.
Now, you tell a lot of great stories in the book and recount some quotes from lots of famous engineers. One of them is George Laurer, who created the UPC system, the barcode system. And I think when he was asked what engineering was all about, he said, well, you just sit down and think through a problem. And I think that's a little bit of a oversimplification of the engineering way of thinking. But could you distinguish how do you distinguish sort of the scientific way of thinking and an engineering way of thinking, right? I mean, obviously engineering requires the use of the scientific method, but in, when we teach innovation at business school, we try to distinguish between kind of invention and innovation. And I think you tell a great story in how penicillin became so pervasive and so effective. And it really wasn't the invention or the discovery that was really the most important thing, but rather the ability to scale it and grow it. And the people who are involved in the latter process are usually, not given the same level of appreciation as the people at the earlier stage in the process.
Indeed, Laura has a fascinating story. Rest in peace. He gave us such a powerful technology that's, I think I've written in the book, his work and that of others have led to kind of immortality. I think I said that every banana, avocado has an imperishable barcoded identity. And
no one knows his name. His name is not up there with Edison and Bell and, Fleming.
It is. And I think there's a broader point that we can discuss. It's one of the elements, oftentimes people confuse the engineering elements and the purpose and the scope to that of science. And you see that playing out even in the COVID-19 work. How much press science respectfully and necessarily gets versus engineering that basically provides a support system on top of which any new science must be built. And I'm even talking about the very technology that's connecting you and me and numerous other listeners today. And of course, the broadband connectivity, the telehealth, and the supply network that we're speaking about, all the invisible kind of the daily grit, the utter ordinariness of engineering systems that are put into place that drive forward any things. Even you use the example of penicillin, how an idea basically became immunity within the span of a few years. This was an idea that was purposeless for a long time. Then the constraint of World War II came in, and public health or preservation was crucially necessary. And then you had the mixing and matching. Margaret Hutchinson, a spectacular engineer who worked in many different contexts. Like she worked in high octane fuel for fighter jets. She led a Persian Gulf installation and a lot of chemical refinery work. But then moving into the realm of public health technologies, penicillin. It's how do you repurpose existing conveniences into fruitful outcomes, and that had significant impact. And you could even see that what's happening with the COVID-19 vaccine. Mm-hmm. How do you convert all the lab notebook formulas into multiple doses in the order of months, not years? Is the question. And one of the concepts that I've recently revisited, and that's really helpful for me to understand the engineering differences from the scientific approaches, goes back to the foundations of the scientific method. Francis Bacon wrote this in 1620, and the New Organon, and there he has a very interesting comparison where he's looking at the different scales, means, types of reasoning. How does one do that? And he compares that to how insects work.
Engineers are the spiders, right?
Yeah, in that, exactly. The ant-like reasoning kind of constant data gathering, collection, accumulation, and separation of arguments versus spider-like reasoning, which is like a spinning of thoughts, kind of webbing of ideas, kind of almost philosophical. Right? And then you have the middle course, which he more than likely meant engineers, because the word engineer has existed since the Middle Ages. The word scientist came into existence only in 1833. So the middle course is the type of done by bees. Exactly. How do you collecting materials from flowers and fields and purposefully shape them to wondrous outcomes. In that regard, so how do you achieve this concentrated nutrition that serves purpose? And you have to again, this is where the notion of responsible, culturally sensitive engineering comes into play. You just cannot harm the flower while you're extracting the nectar. So you have to be careful there. And I think bees have a way of doing that. Responsible engineers also have a way of doing that. So there's a significant difference between understanding the world and doing something about it. And that's where the engineering approaches come in handy.
Yeah, I think we have the same thing in economics, right? So I guess the ants would be the empiricists and the spiders would be the theorists, and the bees, well, I guess they're the people that are doing the policy stuff. But they're not always accepted into the profession as like real insects. But you mentioned that sometimes engineers have to almost misinterpret science in order to get things done. I remember sometimes when I deal with practitioners and I try to explain models to them, and I remember one time I was with a group of consultants from a top consultancy, and I was trying to explain evolutionary modeling, and they completely got it wrong. And I was going to try to fix it, and I was like, oh wait, hold on a second, like they're actually generating all these cool insights from their misinterpretation of the scientific models. How is misinterpretation, sometimes a necessary ingredient to kind of get things done?
It is. And I think oftentimes and necessarily so, scientific outputs do come with caveats and the local conditions and so forth. And you really have to use that as a starting point and then get creative with it. And I think the idea of creatively misinterpreting scientific outcomes for the purpose of engineering, it was articulated by an engineer, Tom Peters, and he has written extensively about it as this is a point of reference for the listeners here. He called it the matrix thinking. How do you go with really multiplying the concepts, transposing the rows and columns? You can seamlessly cut across. You can think about it. In fact, one of the practical examples that comes to mind is where you think about you don't really start off with misinterpreting scientific output or so. It's a common perennial condition until COVID has taught us to reflect on why we have that common perennial problem, which is traffic congestion, right? And one such example that discussed in the book, and one of my favorite ones because it is instantly relatable by everyone, happens in Stockholm, early 2000s. City is facing enormous traffic congestion, and beautiful city, narrow streets, cobblestone, and they have dozens of bridges and roads, and the people are completely frustrated, and they go to the city council and say that this is unacceptable. This is a declining our quality of life. Got to do something about it. And the standard approach is like, oh yeah, let's add capacity to this. Let's add another road or another bridge or something, but that can only take us so far. But if we just let's say hypothetically did a scientific analysis on this, cost-benefit analysis on this, this might have been the most logical, accepted outcome, scientifically speaking. But in practice, it doesn't quite work. So what they did was the city councilors said, let's bring in some external consultants to this issue. And they brought in a bunch of systems engineers from IBM, a company that doesn't have until that point, nothing much to do with the construction or transportation industry. This was before the smart city movement, and they come in and they collect all the data sets, much like the bees, and seeing what influences come from what flowers, what fields, what not, metaphorically speaking, and also did something that engineers sometimes still sometimes shy away from doing it, talking to actual real people. I mean, you have to sometimes remember some of the engineers chose to become engineers because they probably thought they didn't have to work with people. But I think in this case, that was a useful input. So whatever we call as optimization, like achieving the most acceptable outcome within a circumstance, works very well in this particular case study here. And not only that, they also used thousands of photos and survey results, and they built a complete systems model to understand the bottlenecks and whatnot. And they go to the city council and recommend, so nope, you're not building another road, you're not building another bridge. Instead, you're going to start doing congestion pricing. The easy pass thing comes around, and when I go to the airport here in Washington, D.C., I don't even have to slow down below 60 miles per hour. And the camera-based tolling system is just astonishing. It's so cheap, and it automatically debited to my account and whatnot. So this is where, again, some of the scientific elements come in, because you can say that you have achieved a point solution to the problem. But this is where the psychological and social and behavioral sciences elements really come into the picture. If I use the Verrazano Bridge in New York to get to Queens from the New Jersey Turnpike, I picked was $20 each way. That's really expensive for a lot of people. And occasionally we might entertain that expense to achieve some degree of convenience. But if you have a bigger vehicle, trucks, and so you might be paying hundreds of dollars to cross that bridge. This gets to the economic concept of willingness to pay, what economists have later characterized as that, but something that has existed in engineering practice for centuries. What are we actually, even it goes back to Adam Smith's concept of value as he defined in use versus value in exchange. So it's a completely subjective phenomena that engineers have to confront in practice. Will I continue to pay $20 or let's say $30 for a Verrazano Bridge if they increase the tolls for whatever reason? And this is where the psychological elasticity really comes in close contact with the real engineering, hard engineering solutions here. So this is where I think we might need to creatively interpret some of the psychological elements that are now being robustly made possible through some of the research that's happening underway. But the engineers have long practiced the notion of human factors, even though behavioral economics has only picked it up only in recent decades and have achieved fame for it. But good engineers have always put this in practice.
Yeah, well, I mean, you say good engineers. I think what you just described, the Stockholm solution that you described, some would say that that's actually a triumph over the engineering way of thinking, as opposed to a manifestation of the engineering way of thinking, right? All the folks who teach, design thinking out here in California, design thinking, I thought was seen as sort of a remedy for the engineering way of thinking, right? The human factors classes are the classes where you learn to be engineer plus something else, where as Ted Levitt said, people don't buy drills, they buy holes. But the typical engineer is just going to design a better drill. They're not going to look to the what the end goal is.
You're exactly right. You're exactly right. That's unfortunately still a sad truth, because how engineers are prepared to thrive, and yet people are sensitive. They realize what else needs to be done, and I think this is a challenge for bulk of the higher education. What do we consider as a well-prepared professional in a specific area, and so forth? And increasingly, we have to confront the notion of hyper-specialization. How deep do you go in the point? And that's where I was originally trained as a systems engineer. I was rooted in the traditions of controls and efficiency and whatnot. And we can even talk about how efficiency as a method, as an outcome, is completely different than efficiency as a universal value system, which which is omnipresent fairly in efficiency policy, in economics policy and engineering, and increasingly in global health. So one has to really go from it. So in fact, my own evolution from control systems and all of my graduate work in this country have been in complex systems with significant influences from evolutionary biology. So it was interesting. I could track my own changes from a heavily Newton-based approach to a Darwin-based approach. So over time, I've come to advocate for less Newton, more Darwin to become better engineers.
Well, you said physics envy is one of the problems that plagues the engineering profession. But before we dive into that, I wanted to just go back to the story of Margaret Hutchinson, because the story to me is really an illustration of how important it is to combine different disciplines. I mean, she was someone who had expertise in the world of distillation, right? And maybe if she didn't have that kind of background, she wouldn't have been able to figure out how to solve this problem, right? When you look at Gutenberg basically took ideas from the wine industry, right? And how on earth did he get exposed to that kind of technology? When I do programs for corporations, if they come in as a car company and they want to learn something, and I say, well, let's study Netflix, or let's study, and there's initial resistance, like, hey, we're a car company. Let's study, what other car companies are doing. What do we have to learn from Amazon or Netflix? But a lot of the innovation that happens is sort of borrowing stuff from other domains or disciplines. How does that kind of interdisciplinarity, and you mentioned also in one of your articles that not a day goes by before engineers talk about, busting up silos, but it's easier said than done.
That's correct. And, there are so many examples where engineers have found themselves in frustrating circumstances where they're expected to do one thing and they're not allowed to contribute beyond what they're capable of. And the exact opposite, where you expect engineers to contribute a more vibrant, acceptable solution, and then you get a point solution that's useless and probably even backfires. So I think, how do you seamlessly transfer some of the generic ideas across the context is the challenge that we all as professionals have to face. And engineers, let's just not forget because the consequences of engineering, bad engineering, are evident. They're instantly punished, and it's a harshly unforgiving profession. And engineering often comes to news only when something bad happens. Like as we saw that, I mean, it's the Texas blackout was a good example with the weatherization, which was a fairly routinized approach in pretty much many industrial sectors. Yet there are other political factors that prevented such routine upgrades, upkeep from possible. So in this regard, even the idea of, one thing that gets greater press than care and maintenance, kind of the boring part of engineering, which I don't know if there are official studies on it, but by and large, even looking at the investments and the number of engineers involved in such activities, the boring aspects of maintenance and care and upkeep and repair and restoration, as opposed to new, shiny, novelty, innovation type approach. I think oftentimes innovation gets the news and the purposeful recombination, the silent processes that keep the day-to-day operations underway don't get the press. Even
it's hard. So it'd be hard to make a TV show out of that, right? Like, so, ER, somebody comes in, they're spouting blood and, you got to fix them up. But, if you had a really good medical system where everyone was just healthy, you wouldn't be able to make a TV show out of it. Yep. Nothing happened, right?
Exactly. And I think those are the ones that keep the economies running and, or whatever it's worth, the GDPs in their place. It's not the one-off things that really happen. So I think the sheer invisibility of engineering in these processes and the sheer invisibility of engineers such as Laura Hutchinson in these circumstances is something to keep in mind as we think about recognizing individuals and each other within the complex systems that we have created and we operate in.
Well, you describe engineering as using modular systems thinking, and modular systems thinking has such powerful impact in thinking about organizational design, in economics. You mentioned that you've found kindred spirits over in the world of economics when people talk about maximization, constraint optimization, right, mechanism design, and so forth. But when I think of modular systems thinking, I think about that kind of stepwise refinement that you mentioned, and how important that is, and why biological analogies are so important. And you actually authored a really small piece with David Sloan Wilson, right, about complex adaptive systems and complex misadaptive systems. Could you maybe tell us maladaptive systems? Could you talk a little bit about how you began to think about those issues and how you think about them now?
Yeah, and in fact, I'll give complete credit to David Sloan Wilson, evolutionary biologist, for it was a fluke little elective that I took in grad school that they transformed my worldview and made me, I think, a better bioengineer in my own personal grading. And it's the notion of the modular systems thinking, as I articulated in the book, is something that involves surely to understand the interconnections and the functions and the structures of the parts involved. So basic deconstruction. And then you have to put them together as you gain an understanding and depth of the interrelationship between these things, and you put them together, recombine them for a practical purpose. Now, these kinds of processes make eminent sense if you're assembling an automobile or aviation structure or whatnot. And there are standardized processes to achieve these things, where complex systems are engineered. They are not emergent. And that's where the evolutionary concept of self-organization comes in. A system as such, delivers certain services or value or satisfies some expectation, as in the case of democracy, where people have certain basic needs and so forth. So this is the highest level of construction. And so how do you think about evolving a system of democracy? I mean, so you have to operate it at the full composite level rather than a piecemeal level. You can achieve piecemeal optimization, and it backfires when you just assemble them to the top, because each of them comes up with its own vulnerabilities, vagueness, and really the lack of maintainability and so forth. So the system has to be the target of selection, to use the biological metaphor, and then carefully managed in terms of evolving it to its ultimate goal. Not all forms of evolution are helpful. We have all known that, and they have taken us to some extreme circumstances where we find ourselves in puzzling circumstances, and we don't know what to do about certain social developments. But then you have, that's one form of complex system. And then the other form is where each and every system is working well to its spec, basically. Even if it's in a traffic congestion, you can imagine a traffic cop doing his or her work, and then the traffic lights doing their work. So each of them delivering to their specs. But so there's another form of complexity that emerges in piecemeal. But I think the key is to identify when does adaptation, as systems are constructed, engineered, and scoped, scaled, and advanced, become maladaptive. And we learned that one can easily see that in the realm of healthcare delivery, how organizations have achieved a level of refinement, specification, justification, legitimacy in their functions to the point that they are not able to relate to one another. And whatever action one might take squarely conflicts with another. And therefore you have an ultimate maladaptive system from each of these individual adaptive systems. So one has to think about it. And I don't think the engineering systems approaches have quite appreciated that in practice. And I think that that's the kind of the direction colleagues and I see engineering to get better at over time.
So when you say efficiency might be a problem, or the pursuit of efficiency might be a problem, isn't it just a misspecification of the objective function, or rather than a problem with the pursuit of efficiency?
Yeah, and it's interesting because this is exactly the topic that got me thinking just in the past couple of weeks. Which forced me to put something in words. What exactly are we talking about when we mean efficiency? And so that led me to kind of a stepwise refinement, basically, to really understand how efficiency as a concept has evolved. And even the roots of economic theory that are still stable and surviving have a basis in engineering efficiencies, as the if we go back,
the Walras originally, I think, was
exactly, and even before, you have Jules Dupuy and others, as they were thinking about city planning, water supply, railroad taxation, all those things. So there's tremendous engineering economic legacy coming from the practice of engineering.
Mm-hmm.
And the curious thing is, engineers, I think at some point stopped doing that. They came up with cost benefit analyses, analytic approaches, and somehow they've just gone beyond it. Whereas that somehow became the fixed roots of economic theory that we're still grappling with. But to go back to the thought process in which I was applying to the evolution of efficiency itself, at one point, efficiency was basically a toy problem. It started as a toy. It delivered specific local objectives that we're all familiar with. Even the UPC barcode gives us a lot of conveniences that are otherwise not possible. So that's where efficiency works as a toy. And then if you look at the subsequent form of efficiency, it becomes a theory. And this is where the economic policies are rooted in efficiency as in a theoretical way. How cost benefit and cost effectiveness are still de facto methods, fixed static approaches that are trying to improve beyond their control. It's something that we need to think about. Even public health policies are still largely rooted on these static concepts. So that's where the theory part of efficiency comes into picture. The third one is where the theory becomes a tradition, where that's expected wherever you go, and that's assumed behavior. Everyone has to think about efficiency as achieve certain goals, whether it's an organization, you're a chief executive or a politician. And so that's basically now in the air that you breathe, the water that you drink. So that's the tradition I think about. And the final evolution part is that I think a lot of people are beginning to realize. So what was once a toy and still is a toy, and that became a theory, that became a tradition, is actually a trap. And now we find ourselves in very, very difficult circumstances to escape this trap. So that's how I see efficiency, as a toy, a theory, and a tradition, and a trap. So what is the escape path here? And that ties to another piece that I've also recently written when I was asked to think of a world post-pandemic. What is one thing that I wish to see changed as an engineer, as someone who grew up in the doctrine of efficiency? And that's a borrowed concept of what we might call the meaningful inefficiencies. That's I've applied this from work of some civic study scholars, and it's the exact idea of putting speed limits and speed bumps on roads. While I think there are lateral benefits to that. There's safety, psychologically or real applied. Those are the kind of the meaningful inefficiencies we have to install as safeguards so that we don't overly drown ourselves in the efficiency doctrine.
Well, I mean, so just to push back on that, I mean, isn't it just that your objective function is incorrectly specified? So for instance, in the traffic safety example, maybe, you're trying to minimize commute time, let's say, and you're forgetting about safety, or you're forgetting about enjoyment, you're forgetting about aesthetics, or, you're framing the problem too narrowly rather than taking a more expansive way of defining the problem correctly. And I think in your towards the end of the book, you spend a lot of time talking about what engineers can learn from anthropologists, right? What they can learn from sociologists, what they can learn from, people who study people, right? Rather than people who study, stuff. And since you're solving problems for people, it would help to understand the material, of the problem. So isn't this just a call for kind of a broader understanding of the problem and a more creative way of approaching solutions rather than necessarily an attack on efficiency, right? Which is just trying to get more from less.
Absolutely, and you're right. I mean, it's a tight concept. It's a blockbuster concept. It has worked so well everywhere. Who wants inefficiencies in life? I mean, we've all experienced that in a different era of our lives where we used to go to the airports and our baggage, who knows where it is, and whenever it comes out, and all the traffic and getting a taxi out of the thing. So I think these are what we call the mere inefficiencies. But I think the idea here, even this is something that we have learned during the COVID crisis. With a tight concept such as efficiency and a rigid supply network, you can achieve a lot of stable successes. But when you have an atypical circumstance such as the pandemic, you're left to searching what's an ideal configuration for this. And I know there are a lot of supply chain experts who have thought about this, who are thinking about this. What is the future of, and we have been through lean and agile and all sorts of industry practices.
So for instance, if your hospital's running at 99% capacity during normal times, that's considered a good thing. But then, you have a spike in demand and then you're completely overwhelmed, which is what happened.
Exactly. And that's why I think in the UK, and we have similar case studies here in the US, where Formula One company was put into the task of developing ventilators because they knew a thing or two about time-based delivery. No, it's again, as the joke goes, we have gotten so used to just-in-time processes. Now we don't prepare for just-in-case processes, and so that's something to be thought of. And I think there's a lot of recognition, fortunately, because we've all had time to think about, reflect on this. The opposite of efficiency, the way we're seeing it, is not inefficiency, right? I mean, now one has to have a more elastic frame of mind, which goes back to the founding question that you had, Greg. How do you flexibly operate in multiple environments? And I think people are beginning to realize it is actually resilience. That might be a better concept. And the challenge that one comes up with that is, it is the exact opposite of efficiency, even in terms of definition, specificity, and resistance to quantification. So how do we get good at resilience is a question that we all need to think about further.
Yeah. And something you mentioned in the book, which I hadn't ever thought about, was there are remarkably few engineers in politics, right? If you go to Congress, you've got a lot of lawyers, but not a whole heck of a lot of engineers. And you tell the story of Paul Tonko, who was an engineer who entered into politics. Could you tell us again why is that? Why are there so few engineers in the world of politics? And by the way, the most popular class at Berkeley for MBAs is a class called Power and Politics, which for non-engineers is kind of like common sense, but for engineers, it's like eye-opening.
Yeah.
This idea
No,
that,
it's an interesting question. And in fact, the bulk of my job, I've been in Washington for a dozen years now almost. And find myself, there are, of course, a number of engineers who live in DC, but very few engineers who get to do the kind of policy advising that my colleagues and I get to do from the academy. In fact, we were created in the middle of the Civil War by President Lincoln, and one of the first projects that was given to us by the federal government was to provide advice on direction finding of ships, and also even the basic material properties of the ship. How do you make it rust resistant? And also, this was a time when all the wooden ships were being converted to iron ships, and how do you avoid the magnetic interference in the technologies? And so really, it started off as a very practical source of problem. This was the U.S. Navy, basically the equivalent back in the 1860s, having a set of problems. But now the issues that you're thinking about, you're absolutely right. And given how technical engineering still is, by and large, and there are some studies that are also offering motivation to just pause and think about how we pursue the quote unquote training and preparation of engineers. In fact, the work of Erin Sack, who's a sociologist at the University of Michigan, her work and her colleagues have shown that how engineering education has become overly technical to the point that even within the 4 years of preparation, the public welfare concerns of students significantly decline.
But engineers are good at engineers understand trade-offs. They understand constrained optimization. Isn't that what politics is?
In a way, but I think the outcomes are sometimes hard to say because the negotiations are constantly happening, whether one likes it or not, or there are undeclared preferences, and I think that's a complicated thing to imagine. This goes back to the complex maladaptive systems concept, where one system works completely fine according to the spec, well-defined trajectories, but it goes against the notions of something entirely different. And the examples of David Kuhn that you've used, and Paul Tonko's congressman here, and very few engineers, also like to point out that this might be a cultural phenomenon. If you look at the number of engineers in politics of China, a lot higher, and that may suggest how the governments respectively choose to prioritize the maintenance and infrastructure differently than other countries. And there's also work done by Michelle Gelfand, who's an organizational psychologist, University of Maryland, soon moving to Stanford University. Her pioneering work on tight cultures, hierarchical, well-knit versus loose cultures, and how they go about their social priorities is eye-opening. I mean, even very recently, we have learned how Bhutan, the Hindu kingdom, as it's known historically, had no casualties because of COVID, and how tight cultures have approached COVID in a very different way than, let's say, loose cultures such as the United Kingdom and the United States. We have had far more casualties because of COVID. So the point here, I think the overarching point here is like, how do you, there's the cultural phenomena of engineers choosing to engage themselves in politics. But if you want to get real philosophical about it, engineering is politics by other means. You don't have to run for elected office, or given the kinds of influences some of our technologies or kind of the platforms have had in recent years, notably and disturbingly so. One has to think about what kind of influences it has. In fact, it's even the practice of engineering. If you go back to the kind of, this is a civilizational point. We were probably doing engineering before we were constructing government. So engineering is arguably older than the concept of democracy.
And you mentioned that engineers are often attracted to extremist points of view because they're kind of closed systems.
It is, yeah. That was a disturbing analysis, and I think I discussed that in the book about how being so outcome oriented, good or bad, sometimes is could be lethal, and could be threatening for the social fabric. And I think to be in politics, you have to, of course, this is such a generic point that I'm making. You have to be smooth around the edges, not be so fixed. I think that's why I think it's a complicated phenomenon where engineers are professionally so attuned to making sacrificial judgments when it comes to certain forms of design, but not when it comes to civic matters. That's an open puzzle. And Greg.
Well, one of the things that I notice in my engineering students is that, they do want these definitive answers to questions. So in economics, it doesn't seem to be that much of a conflict. But once we get to kind of the world of strategy, where, there are known unknowns and unknown unknowns, and, that you're basically making decisions with a high degree of uncertainty, that's where engineers begin to start encountering the limits of their normal way of thinking. So once you start learning about strategy, then it becomes kind of engineering plus.
It is. So and I think it's the sheer adaptation, the versatility of the engineering mindsets that's so appealing, that makes it more portable across contexts. But you're also right. I mean, how do you? It's also the ability of engineers to engage with the degree of blatant uncertainty and vagueness, and the vagueness often posed by word choices more than technical choices. In this case, how people choose to describe a system, or their even their wants and needs. So that makes it a little bit complicated.
So I read an account by a public health expert recently who said that with respect to COVID, what we need is an engineering solution to COVID. And we have not been thinking like engineers with respect to this problem, right? Where you have a clearly defined objective, and then you figure out the best way to achieve that objective. Throughout the crisis over the last year, it's never been clear exactly what the objective function was of our policymakers. And so do you see the crisis, the COVID crisis of the last year as a failure of the engineering mindset, or a failure to use the engineering mindset in policy circles?
I think it is the latter indeed. But I think this was a predictable one. I mean, this could have been forestalled. Indeed, we have a lot of experiences. Also, it goes back to the notion of how, by properly deploying engineering practices, insights, wisdom to complex systems, to better engage with complex systems such as COVID, we also have an opportunity to improve the practice of engineering on the go. And we saw that even with the precursor Ebola crisis, about how if you take the standard efficiency-based metrics, cost-benefit, cost-effectiveness approaches, you just completely fail to even advance vaccine candidates that were available but just sat on the shelf for over a decade and not available when it was. But in this case, we have a novel pathogen, even though there's heritage for it. I think the key was how do you readily bring in resilient supply practices. One example that really disturbed me, and this was also subject of a congressional hearing recently, maybe some months ago, was how a mid-sized firm with the Chinese equipment to manufacture masks, millions of masks when most needed, couldn't do it purely because of incompatibility of the products that they were receiving. And we are not talking about melt-blown polymer not being available or anything like that. It was basically fixing the ear loops with the mask, and the ear loops basically came in a wound fashion, and the machinery was not able to unwound it and properly use it. This is the kind of utterly basic dysfunctionalities we have had to deal with when we couldn't produce masks on time at the volume it was needed at one point. So that's why it's there are a lot of experiences, established practices within the strictures and highly regulated environments of engineering that we might be able to harm. So now one argument some might pose, well, that's just a problem of physics, well-defined outcome. You can achieve exactly this and then do that. But how do you go about in an unforeseen circumstance kind of thing? Even though this was all predictable, we have heard stories about how so many wargamings were conducted on these kinds of scenarios before. So this is where I think the brute force engineering solution is not going to work out well, which means a modified, adapted, and more sensible form of engineering is needed. And I think this pandemic gives us still an active opportunity. It's not over. I think to try that in real time.
And one of your recent articles, you called for a professional responsibility for engineers. And I hadn't really thought about, I wasn't aware that there was such a thing, right? I mean, I was trained as a lawyer, and professional responsibility was a course that we all had to take. And it's something that you have to take an examination on it to become a lawyer. And of course, doctors have professional responsibility. Journalists used to have professional responsibility. But as far as I know, no one takes a course on professional responsibility when they're getting their engineering education. And it's certainly not something that you have to be examined on in order to become an engineer. But you detail some things that you think every engineer needs to think about with respect to the impact that they have on the world. Could you talk a little bit about this? And could you foresee a time when engineers are required to have some kind of professional responsibility certification?
Yeah. So this is an interesting question. There's a lot of history to this subject as well. I mean, I think most engineers should be able to talk about the Code of Hammurabi from some time ago, where the builders need to sleep under the building, under the bridge, or inside the house, so that if it crumbles, I mean, that's the basic, the blunt form of punishment here. And we have codified concepts. The National Society of Professional Engineers has such rules. Now, how do we? And I think it all fundamentally relates to the notion of accountability. And there are a lot of circumstances where we can, we find the designers and the deployers of technologies just get away with the things. But this is not in a kind of a punitive sense, but this is how you think about the scale of consequences that engineering comes with, because it is in contact with the reality and intergenerational consequences. Climate change, I think it's one thing that we are still trying to understand how to proceed further, even though there are a lot of stable signals pointing us to the directions of emission reduction and so forth. And of course, to be objective, I think a lot of engineered technologies have contributed to this. So in this regard, I try to move away from the standard definition of engineers as problem solvers. Doesn't work too well for me when equally we have been problem creators. So one has to be sincere about this. And that's why even at the National Academy of Engineering, we are taking the concept of we are moving beyond the notions of just ethics. How should an engineer behave in a certain situation or not? So that's a very situational ethics framework. And one of the programs that we are creating, it's called CSER, Cultural, Ethical, Social, and Environmental Responsibility in Engineering. Really looking at the character that professionals need and the profession needs to really think about it. And of course, touches on a lot of philosophical concepts and humanities and sociology. So we are trying to bring those concepts widely into the practice of engineering beyond the legal and the regulatory strictures that we're talking about. So there's much more work to be done in this area and emphasize professional responsibility rather than in a code of conduct.
Well, I appreciate you for introducing me to this journal, the Philosophy and Engineering, which I did not know about before. So before we end, could you tell us a little bit about your new book, Making Better Choices? Making Better Choices?
Yeah, Making Better Choices. The subtitle is Design, Decisions, and Democracy. And this is co-authored with...
Is it just because you've been in Washington for so long?
Charles Phelps, yeah. And it's coming from Oxford University Press. It's slated toward an academic, maybe, I don't know, mixed market audience, not a popular nonfiction like Applied Minds that we were talking about earlier. But this grew out of the question. I mean, it's a fundamentally a human factors question. What are the most essential elements when it comes to making decisions as an individual, electing someone to represent them in whatever form, or you're making a decision as a group, or whether it's an organization or your local civic club or whatnot? It comes down to the idea of do we have enough expressivity in the tools that we have gotten to rely on over time. The most common one is, of course, the vote for one approach, which we use in elections. And I think there are a few countries and the constituencies that are beginning to think differently about it. The sheer, the counting the volume of votes. I mean, that's basically the democratic approach in most advanced countries, and there's approval voting, choosing who you select, and then you have rank ordering. So you have a lot of grading, sorting, and those kinds of approaches. And we wanted to, in one practical context with colleagues, we decided to compare these voting methods and see what works well. And in that particular case, and this was a study that we did and reported in the journal Nature a couple of years ago. And that got published around the time of the U.S. Presidential elections that led to Trump's victory. And it came out at an interesting timing to really look at if the voting methods that we use are appropriate. And of course, the U.S. has a very different structure, the Electoral College and so forth, but still the general idea, whether you're doing a department level decision or if you have a county level decision, I think the idea applies. What would it take to improve the electoral participation, which I think is a serious issue. Perhaps a lot of people are disengaged because they don't have the mechanism to express their viewpoints through the existing tools. So if you put a systems engineering viewpoint on this subject, and which is the entire thrust of this book, you begin to think about many different layers. What is the experience one has when you use, workflow? What are the engagement opportunities with it? And does that and enable you to fully express your points and so forth. So we did a lot of on the ground studies, and that led to this overarching concept of design decisions and democracy. I think it is just a reminder saying that if you take an engineering approach, we quickly realize the inadequacies of the tools that we use, and we just have made a tradition out of. And I think this is not engineering from the perspective of, yep, here's a key for your door, but rather using as an intellectual foundation to think about the approaches. And that's what the systems engineering is about. Oftentimes, systems engineering doesn't involve producing a solution at all. Like, let's say, more specialized forms of engineering. It is about gaining a greater appreciation of the kinds of trade-offs we are willing to make going forward to achieve practical consequences that at the same time are responsible and we can justify and support. So that's the general idea. So this is systems engineering meeting social psychology meeting political science kind of experiment that we were fortunate that the Oxford University Press gave an opportunity at the press for.
Well, that sounds like my kind of book. Can't wait till it comes out. Guru, really appreciate you speaking with me today. This is the book, Applied Minds. There's a lot of great stories in here about how, time zones were created and how penicillin was created and how the barcode scanner was created, the cell phone, just a lot of really wonderful stories packed into a really short book with a lot of thoughtful discussion of how engineers think. So thanks so much, Guru. Talk to you again soon.
Greg, thank you so much. I enjoyed this.
This is Unsilo, brought to you by Alumni FM, connecting people through stories.